Welcome to Noble's tutorial. On today's chemistry, we'll be talking about nuclear chemistry, otherwise called radioactivity. Okay, why some people refer to it as radioactivity? Because it happens in the nucleus of an atom. Now, what is radioactivity? Radioactivity can be defined, as seen on the board, as the decay, the disintegration of the nucleus of an atom, radioactive elements in that matter, with the emission of radiation and energy. Now, to further bring your mind into this radioactivity, as interesting as it is, you cut across physics and chemistry, and do well if you understand it in any of this field. Now, radioactivity as a subject was discovered by a French scientist called Henri Becquerel in 1896, when he was observing an uranium ore and observed that it emits radiation in his course of research. A follow-up research was done by Pierre Curie and Marie Curie, husband and wife, chemists, okay, and that was in 1898. In the course of the study, Pierre and Marie Curie tried to isolate other important radioactive elements, having discovered that a pitch blende, which contains uranium ore, emits more radiations far than can be accounted for by the uranium content. So in further investigation, they discovered that the pitch blende do not only contain uranium but contains other radioactive material. So they engaged in research trying to isolate those radioactive elements. And in the course of the research, Perry was exposed to radiations and he died at the spot. Marie Curie, being the wife, continued with the research and was able to successfully isolate polonium and radium, in addition to the thorium that she and her husband did initially. And for that conclusive and well done job, the Chemical Society and the scientists put together and agreed to award her a Nobel Prize in chemistry. And she was the very first person to be given a Nobel Prize in chemistry. And that will lead us to talking about types of radioactivity. There are two types of radioactivity. We have one, natural radioactivity, and artificial. As the name implies, natural radioactivity occurs on its own in a radioactive element spontaneously and continually on its own without being aided by any cause or anything. But in the other hand, and in the course of that radioactivity, of course, radiations and energy are liberated. Energy is given off. Now, in the case of artificial radioactivity comes as a result of bombardment of the nucleus of an stable atom, thereby creating a radioactive isotope which is unstable that can undergo further decay in the process, which can be utilized in course of research. Okay, and this will lead us to it will lead us to talking about the different types of radiation. But before we continue, I would like you to please subscribe for more information on Noble tutorials. Now, the different types of radiations. Quickly, let's look at the three main types. We have different types, but we regard three main types of radiation. There are three main types. three main types of radiation. The first, we talk about alpha, in brackets called alpha radiation, or you call it alpha particle. We call it alpha particle or rays. And next we have the beta radiation. Beta radiation, or you call it the beta particle or rays. And lastly we have the gamma radiation. We call it, this time it is not called gamma particles, but it's called gamma rays, because it does not have mass, does not have weight. Okay, so it's called gamma rays. And among the three types of radiation, gamma rays are the most penetrating of these three. Then alpha ray has less penetrating ability. It can be represented by the nucleus of an helium atom. Okay? So let's quickly take a look at each of them and their symbols. Okay, like the gamma rays represented by this letter gamma. Okay? And alpha rays by this alpha letter, and beta rays by this beta letter. So in the course of the radiations that are produced, if an element undergoes an alpha decay or produce alpha radiation, it means that the element will emit alpha particle. At the same time, if an element undergo beta radiation, it means that the element will produce or liberate beta particles. The same thing happens when an element undergo gamma radiation. It liberates gamma rays. So that will lead us, we need to understand how the symbols work. An element with mass A, an atomic number Z, if it undergoes an alpha decay, if it undergoes an alpha decay, it gets to lose 4 from the mass. So from here, you say A minus 4, and it will lose 2 from the atomic number, that's Z minus 2. Let's say the new product, the daughter nucleus that is produced is Y, from X to Y. And in that process, it will liberate an alpha particle, which is represented by an helium atom. This is an alpha particle, represented by an helium atom. The same thing happens if an element undergo the same, let's say the same element undergoes beta decay. Beta decay. It will liberate a beta particle, which is presented by the symbol of an electron. Okay? That's a beta particle. It's presented by the symbol of an electron. Okay? So in beta particle, nothing is added to the mass, so the mass remains the same, but 1 is added to the atomic number, so that will be Z plus 1. This shows gladly alpha decay, beta decay, but in that of gamma decay, there is no shortage in the mass or addition in the atomic number. In any case, so if an element undergo, say, an alpha decay, a gamma decay, it remains the same. The daughter nucleus remains the same, but with the liberation of gamma particle. Now this will now lead us to talk about, like I say, please, to get more view, to get more of our tutorial, it is important you subscribe to our YouTube channel. Okay, Noble Tutorial is our YouTube channel. So to see more of us. Okay, then this will lead us to talk about the laws of radioactivity. There are two main laws of radioactivity. Quickly I will discuss them. The first law of radioactivity is dependent on this word alpha decay. And the second law is dependent on this word beta decay. Now, so this one will help us to imply the first law of radioactivity. And this will help us to imply, the beta decay will help us to imply the second law of radioactivity. Now, Aaron says that, like I said earlier, it's important, please do subscribe to our YouTube channel, Noble Tutorial, to get more of this information. Quickly, I would like to state the decay series from where you can understand when an element undergo an alpha decay following the first law. What are the likely products? What are the new products? From how do we arrive at those new daughter nucleus that is being produced? Okay, so quickly, I will outline the decay series. The decay series, so that we can understand in this decay series, I use a poem. Radioactive elements begins from the periodic table from lead, atomic number 82. I use a poem so that I can be able to recall, and it's easier for you. And it will help us to be able to arrive at the new daughter nucleus when we are trying to explain the radioactive decays. Okay? Lead, which is atomic number 82. The atomic number is more important here. I use the word leaders. And the next radioactive element, which is bismuth. Leaders, I use the word beats. The next, which is 84. Leaders beats, that is polonium. I use the word politicians. And the next, which is leaders beat politicians, arts, that is astatine. At random. At random. The next person is random. That's random. Atomic number 86. Leaders be politicians at random from, that is for Francium. From 87, rays, that is radium. 88, rays, action. 89, action. Though, atomic number 90, that's for thorium. Though, partisan. Though, which is for protractinium. Though, partisan, atomic number 91. Partisan umbrella, that is atomic number 92 for uranium. Neptune Pluto. Just put it somewhere. Atomic number 93 and Pluto atomic number 94. These are the lists of radioactive decay series. These are the elements. If for instance I say an element undergo 2 alpha decay, let's say uranium atomic number 92 undergo 2 alpha decay and 2 beta decay. What is the stable nucleus that is being produced? So the stable nucleus, according to the first law of radioactivity, that states that, which is alpha decay. For instance, I say that if an element undergo, the first law of radioactivity states that if an element undergo alpha decay, the total nucleus will be found 2 places to the left. So you count backward from the parent nucleus, 2 places to the left of the parent nucleus on the periodic table. Then if, according to the second law, that if an element undergo a beta decay, the total nucleus will be found 1 place to the right, which is 1 step ahead, 1 place to the right of the parent nucleus. So if I give you, for instance, I say an element undergo 2 alpha decay, what is the stable product? Now 2 alpha decay means it loses 2 alpha particles. According to this law, let's say uranium loses 2 alpha particles. Uranium will go, the first alpha particle will be 2 places to the left, that's backward, 2 steps backward from the parent nucleus. So 2 alpha particles will go 1, 2. So the stable nucleus for the first step will be thorium, and then you move 1, 2 from thorium. So the most stable nucleus there that will produce after 2, this one, this is the first alpha decay, and the second alpha decay. So the stable nucleus that will produce, if we are to represent it in equation format, will be we say 2 alpha decay. For if uranium, let's say uranium 238, atomic number 92, undergo 2 alpha decay. That means remove 2 alpha particles. Okay? 2 alpha particles, which is 4He2. The stable nucleus that we produce is, which is radium. You remove 2 times 2, which is 4, remove it from 92, you can see it will give us 88. Then 2 times 4, which is 8, you remove 8 from 238, you see it will give us 230 radium plus N.H. Now this represents 2 alpha decay. When uranium 238 atomic number 92 undergo 2 alpha decay, this is the equation representing that nuclear reaction. This is the equation. One thing you must know is that the law of conservation of energy, the law of conservation of matter must be observed. So the total masses on this side must also balance with the total mass of the product. That is the total nucleus. Even after adding the particles with the total nucleus, they must balance. By the time you multiply 2 times 8, 2 times 4, sorry, that will give us 8 plus 230 to give us back 238. And 2 times 4, which is 2 times 2, sorry, which is 4 plus 88, it will give us 92, balancing the masses and the atomic number, which clearly shows that the law of conservation of matter has been observed. That law that states that matter can neither be created nor be destroyed during the course of any chemical or nuclear reactions, but can be transformed from one form to another. Okay. Then if an element undergo beta decay. Let's say radium atomic number 88 now undergoes 1 beta decay, for instance. It will follow the second law of radioactivity, which says that the daughter nucleus will be found one place to the right of the periodic table. Now if you look at this, if an element undergo 1 beta decay, it will move from let's say radium is undergoing 1 beta decay, radium 88 atomic mass or nuclear mass 238. If it undergoes a beta decay, the daughter nucleus will definitely become actinium, which is AC atomic number 89, which means it moved one place to the right of the periodic table. Then the mass, being that beta particles has no mass, so the mass will remain the same, 230. Clearly showing that by the time you add -1 plus 89, it gets back to 88. And then of course energy is liberated. This explains the second law, whereas this explains the first law. This explains the first law. Okay, having discussed this, it is eminent I also tell you about half-life, that is rate of decay of a radioactive material. Half-life of a radioactive material, which from there we can. So please do subscribe to Noble Tutorial for more of these videos. Half-life of a radioactive material is a time taken for the total mass of the radioactive material to decay into half its original mass. So the total time taken for the mass, the entire content of the mass to break, to be left with half of what it started with when the radioactive material undergoes or do perform radioactivity or undergo radioactive decay process. That is referred to as the half-life of that radioactive material. For instance, if I have 400 grams of a radioactive material, say X, and it takes, let's say, 5 minutes. It takes 5 minutes for these 400 grams of the radioactive materials to break down to 200 grams of X. 5 minutes become the half-life. 5 minutes become the half-life of this radioactive material X. Time taken for it to, from the original mass to break to half of what it is. Now a question can come up and say, what mass of a radioactive material, like it can be asked in your WAEC and in your JAM questions, what mass of the radioactive material, given that the half-life is 5 minutes, will be left after 15 minutes of decay? What mass will be left? Now, what mass of a radioactive material, let's say 400 grams of X, will be left, given that the half-life of the radioactive material X is 5 minutes after 15 minutes? You will take it in steps. The first half-life will be from 400, you break it down, half of this after 15 minutes, after 5 minutes, we are aiming at 15 minutes. After 5 minutes, it becomes 200 grams. After another 5 minutes, every 5 minutes interval, which is a rate count, after another 5 minutes, this will break down to 100 grams of X left. After another 5 minutes, that will make it total of 15 minutes. After another 5 minutes, it breaks down from 100 to what? 50. So if you ask what mass will be left, the mass that will be left after the total time of 15 minutes, the mass that will be left will be what? 50 grams of X will be left after 15 minutes. Following the first principle in calculating the half-life. There are other ways that this can be calculated using the formula. Half-life, that is the new mass, the total mass all over the original mass, is equal to 1 all over 2 raised to power the total time all over its half-life. Now, if the original mass was 400, you substitute 400. This is the mass that will be left, which is what you are looking for. Original mass is 400, so N, the new mass, all over 400 is equal to 1 all over 2 raised to power. Total time taking is what? 15. 15, while the half-life here is what? 5. So 15 over 5, and then you get 15 divided by 5 gives you 3. So that again will lead you to, that is another way to resolve this in some complicated cases. That will lead you, if you look at from this point, you are having that N1, which is a new mass, all over 400 will be equal to, this goes here, it will left to 3. So 1 over 2 raised to power 3, which is the same as 1 over what? 8. You cross multiply, and then our N1 we multiplying 8, and 400 we multiplying 1. So that's 400 times 1. So get N, you divide both sides, N1 you divide both sides by 8. So 400 divided by 8, 8 in 40 will give us what? 5. With a 0, that will be 50. So the mass that will be left after 15 minutes will be what? 50 grams. Just like we calculated using first principle. Very important. There are some complicated cases that the first principle will not have given you, but by the time you apply this formula, you can always be able to get it. If they give you a total, it spans over a total range of time. It's more convenient to use the formula. But if the total time taken is shorter, then it's more convenient to use the first principle. Please, like I said again, do subscribe to our YouTube channel, Noble Tutorial, for more information. And lastly, I would like to drop for you, you can also calculate half-life of a radioactive material if you are given the decay constant. You use the formula 0.693 all over the decay constant, where lambda represents what? The decay constant. The decay what? Constant. Lambda represents the decay constant. And if in a case you were told what mass has decayed off, you started for instance with 400 and you have lost in the course of what is left after 15 minutes, you now say the original mass minus what is left after the whole decay series, and that will give the mass that has been decayed off. Like in this case, it will be mass decayed off, that's change in mass, that's delta N. Mass decayed off would have been that original mass minus the new mass. which is 400 grams minus 50 grams. So the mass decay of, in this case, is 350 grams after the radioactivity that has spanned for 15 minutes in this case. This represents the mass decay of, which can also be used to calculate the bond energy or the binding energy that held the atoms and the energy that is released in form of radiation and also in form of heat. Now, radioactivity has its application spanning from the field of medicine. Radioactivity is used in treating medical conditions, okay, like cancer of the blood. It can be used to treat tumor, the thyroid, the swelling of the thyroid. Use copper-60 to treat that. The cancer of the blood, we use phosphorus-32, okay. These are radioactive isotopes that can be used, that produce radiation, that can be applied in radiotherapy to emit gamma rays that can be used to destroy cancerous cells. Then again, radioactivity is applied in industries, okay, to calculate the expiring dates having produced your product. What to estimate the expiring date of your product. Apply radioactive techniques. Radioisotopes and radio techniques is applied to calculate the expiring date of the product and giving you the time to be able to, you know, how long your product should stay in the store or your product should be out in the market that it will be good enough for consumption. And radioactivity again is applied in medical field or in industries for sterilization. Okay, while during packaging. Okay, sterilize equipment, surgical equipment to free them from bacteria and from viruses. Sterilize them, okay, by exposing them to radiation. You package it, and since the radiation can penetrate through materials, it kills if there is any remains of microorganisms in that equipment. So it kills the microorganism and render it, the container, totally sterile. So radioactivity is very important. It has very wide range of application. Even in the field of agriculture, radioactivity is used to induce mutation that has advantage product, to increase the durability of product, to increase the taste, the quality of the product. The crops are exposed, okay, to radiation to cause genetic mutations that are applicable, that has advantage, okay, and that are good for, have better benefits and better health benefits, and also have more profit margin, okay. Radioactivity, on the other hand, can be used to produce steady electricity, okay, like the submarines that moves underneath the water. You don't expect it to get oxygen when the people inside the submarines need to survive with oxygen. So radioactivity or nuclear reactors are used to power the submarines, okay, that enable it to move even months and go over years underneath the water without the need of external source of electricity, because it produces on its own enough energy that can be converted, okay, to a source of electricity. Radioactivity can also be used to produce weapons of mass destructions, okay. Advanced nations use it to warn their enemies that they have advanced technology in case of invasion, okay. When your enemies realize that you have more superior firing power and you have weapon of mass destruction, they won't want to tamper with your citizens or with your territory. So that again keeps a nation safe. These are various ways and various applications that radioactivity can be used, okay. Please do subscribe for our YouTube channel, okay, to see more of our tutorial. I remain my humble self. I'm James Godwin Igbomifonke. Thank you for watching.